Okay, so I'd like to spend a few minutes going over these problems for chapter 11. There are only 4 problems. The last one's a little bit of a challenge. The first 3 are not difficult at all. So recall, we just barely touched on this, but I think if you have a little bit of feel for what momentum is and this relationship between objects in rotation and angular momentum as opposed to linear momentum, angular velocity as opposed to translational or linear velocity and so forth, I don't think it's that difficult to understand. Maybe you'll let me know. L is equal to, that's the angular momentum, that's equal to I omega. Omega is a vector, so is the angular momentum. Angular momentum is conserved, always. So if you put your fingers of your right hand in the direction of rotation, your thumb gives you the direction of the angular momentum. Because in a few of these problems they ask for the direction of the angular momentum, so it's that right hand rule. Number 1, a spinning sphere. Well, L is equal to I omega. The only little bit of a challenge here is finding I of a solid sphere. You can look that up, just Google moments of inertia, and you can find the moment of inertia for a solid sphere, and I think they give you the angular speed, and just, it's dead simple. Number 2. Same problem, except in this problem for number 2, it is a disk, so you have to find the I of disk. Okay, sounds like some witch's brew. Bring me an I of disk. All right, number 3. For number 3, it's a cute little problem with Big Ben, a clock. Okay, so you have the hour hand and the minute hand. Okay. And they're going round and round. And as you know, the minute hand goes around once every 60 minutes. The hour hand goes around once every 12 hours. And what you need for this is that the I of a long, doesn't have to be long, a thin rod of length L and rotate it about its end, I is equal to 1/3 ml squared. Okay? So knowing that, they give you the length, they give you the mass. You can calculate the angular velocity by knowing that this goes around once every hour, this goes around once every 12 hours. So they're constantly in motion, and angular momenta are vectors. They add just like vectors. These are both going in the same direction, clockwise. So the total angular momentum of the hour hand, of minute hand and hour hand, they sum up. If you had one going in this direction and one going in that direction, it would be the difference of the two. Okay? That's number 3. For number 4, I'm drawing a top view. There's a turntable. Here's the axis of rotation. They say it's a cylinder. The moment of inertia for a cylinder is the same as a disc. A disc is just a thin little piece of, cross-section of a cylinder. So for a cylinder, a solid cylinder, the moment of inertia is just like a disc. It's mr squared over 2. So this thing's rotating. It doesn't really matter the direction. I think it's rotating counterclockwise. And they give you omega initial. So here's this turntable rotating happily along. And then this is sometime later. The turntable doesn't change, but someone drops a piece of clay onto the turntable. Now, they don't drop it like from, the top of the Empire State Building. They drop it from a little tiny distance above. Doot. It hits the turntable and sticks. This distance is R, and I'm going to call that little m. What's going to happen? Let's just think about the physics. This turntable is turning on a frictionless bearing. Nothing else is going on with that. And as that clay sticks, it's going to slow it down. You've got a perfectly inelastic collision. The piece of clay came on there and stuck, and now it's going to turn more slowly. But let me draw this as omega final. So this is post clay. So now the clay is stuck to it and the table has slowed down. All right. Momentum is going to be conserved, angular momentum. This little bit of clay started out with 0 angular momentum. It was just stationary and it was dropped. So L initial is equal to L final. It really should be vectors, okay? In this case, I don't have to worry too much about the vectors. Both omega initial and omega final are going to be counterclockwise. I know that since this was dropped vertically, that it's not going to stop the turntable and make it go in the other direction. If somehow this piece of clay came in and was headed this way, then it would have some initial angular momentum about this axis, and you would have a collision, and it may turn the table the other way. But being dropped from above, just dropped on, it's just going to slow the turntable down. All right. So what is the initial angular momentum of the system? L initial is simply equal to I of the, I'll use TT, I of the turntable times omega initial. What's L final? L final is equal to I of the turntable, that didn't change, plus I of the clay times omega final. That clay, since it's stuck to the turntable, it has an angular momentum and it has a moment of inertia about that axis of rotation. This is a point mass. This is a point mass. So I of the clay is going to be m little r squared. So that's the mass of the clay, and that's the distance squared from the axis of rotation. That clay was dropped in a little bit closer to the axis of rotation than the edge of the turntable. So omega final, I'll just write it down here. Omega final is going to be equal to, since you set these equal to one another, I of the turntable divided by I of the turntable plus I of the clay, and all of that multiplied by omega initial. So you do that calculation, that's simple. For part B, I think they ask, is there a change in kinetic energy? Absolutely. Because you have an inelastic collision, kinetic energy is not conserved. Angular momentum was conserved, but the kinetic energy of the system was not conserved. So there is an inelastic collision. KE is not conserved. Okay. So find the change in the kinetic energy, delta KE. You need the the final kinetic energy, which is 1/2 I of the turntable plus I of the clay times omega final, which you calculated, omega final squared, which you calculated in part A, minus the initial kinetic energy was just 1/2 I of the turntable times omega initial squared. You're going to get something negative, okay, for this calculation. The final kinetic energy is less than the initial kinetic energy. And in all these inelastic collisions like this is what happens. There are losses due to that collision. That energy went into deforming the clay, it went into sound, it went into heat. Okay, all these kinds of things. All right. Part C. For part C, I think it's just a yes or no question. But for part C, you're asked, is the system's momentum constant? What they're talking about is the linear momentum. All right? Angular momentum was constant. The L initial equals L final. But the linear momentum of the system did change, all right? Because that system, you think about, okay, what's the system? Well, this turntable's attached to the earth and all of this stuff. And so when that little piece of clay was dropped on there, it definitely had a change in linear momentum. We're going to ignore the little drop, but it got accelerated very, very quickly after the collision. So there is a change in the linear momentum, and so this answer is no. I mean, you've got a multitude of tries. This answer is no. The system's linear momentum is not constant. Okay? Turntable, when you think of turntable clay as the system. So delta P, for part D, they said, well, calculate the impulse. We know that the impulse from way back Well, it wasn't really way back, it was a little while back. The impulse is the change in momentum, all right? So P final for the little piece of clay is equal to little m r v final. Okay? Oh, I'm sorry. Little, it's equal to little m v final. V final is equal to little r omega final. So P final is equal to m r omega final. Okay. And I'll let you calculate that. And, you know, I think they asked, is the direction of the impulse, so the impulse by the turntable on the clay, well, it accelerated the clay. I think they said, you know, you're dropping this, if we're looking at the top, from a top view, you're dropping this at the east point, so that impulse was north, I think. Okay. If you have questions, let me know.